Alrighty, so in the last class, I told you the heat. I told you the difference between the heat and temperature. Heat and temperature. So heat and temperature. So I told you heat is energy, so it can do the work. Heat is energy, it can do the work. But temperature is just the effect of the heat. How hot is something or how cold is something, like the degree of hotness or coldness. So in the real life, everyday life sense, this temperature is not that important. Heat is really important. So what everything we do, what we are doing in our body or outside, we are using the heat energy. Yeah. So heat produces some effect that is called the temperature. So temperature is not that much important for us. Heat is really important because heat is the energy and it can do the work. Yeah. So heat is a energy. So heat is a energy, and this energy always flows from hot body to cold body. So you have a hot body there, you have a cold body here. So if I connect this hot body with the cold body with certain wire, it always flows from the hot body to cold body, higher temperature to lower temperature. Yeah. So it is a kind of energy. It always flows from the hot body to cold body. Make sense? Good. So, and the temperature is just the degree of hotness or coldness. Degree centigrade, degree Fahrenheit. The unit of heat is joule, kilojoule. The unit of temperature is degree centigrade, degree Fahrenheit, Kelvin, something like that. So, all right. So this is what I told you, and we were in the slide number. I was talking with about the system, boundary, and the surrounding. I'm in the slide number 7, and I told you what is system, what is surrounding, and what is uh, boundary. So anything you take, anything. So whatever you want to take it here and study, that is called system. And everything outside the system is called surrounding. So surrounding. So surrounding here, and then the thin line here, that's separate the system with this surrounding is called the boundary. That's what I told you. Yeah. So suppose I was teaching the thermodynamics course, whole thermodynamics course in UW Milwaukee, couple of years before I come here last year. So there are a lot of questions in thermodynamics. So to identify systems, surrounding, something like that. So let's take some of the examples. So I have a cup here. This is a cup, and I have water here. I have hot water here. This is hot water. This is hot water, and what is system here? So what do you want to study? That is your system. So somebody may want to study only water here. So if you want to study only this water here, that is your system. Makes sense? But if you want to study together, the vapor going out and the water, this one, so this becomes your system. What you want to study. And if you want to study this vapor, this water, and this cup together, then this becomes your system. So what you really want to study is the system. Make sense? So it's all you define yourself. Okay, I want to study this one, so this is my system. Make sense? So, and rest of the things are the boundary. So let's take one more example here. So, so this is our heater here. In our home, we have a heating system, right? So what they do is they send the hot water from. So they have the boiler in the basement. So they send the hot water in this pipe in our apartment. So this is hot water, and this is a pipe, and this pipe comes like this. The water comes like this, goes like this there, and this is our room. This is our room. So this just gives the heat out in our room here like this. So like this. So what is system? What is boundary? What is the surrounding here? So if you want to identify that one, so somebody who is expert in the only studying water, he may want to study only water. Oh, I don't know about anything about this pipe. I don't know about anything about your room. I just want to study the hot water because I am the expert in the heating system, the hot water system, right? So he may want to just study the hot water. So that is his system. So somebody just want to study this water, flowing water here, and that is his system. Make sense? System. Now, but somebody may say, oh, I know this, I know all about this water and I know all about this pipe, right? So somebody can understand both how the water behaves and how the pipe behaves. So he may want to study both water and this pipe together, and then he defines, okay, my system is pipe as well as the flowing water. Make sense? Just what you want to study. And somebody may say, okay, I am the expert in everything, so I am going to study together my pipe, this pipe, the water flowing in the room. So all this room, so that becomes the system. So whatever you want to study together, that is called a system. Make sense? But if somebody say, oh, I just want to study the water only here, so this pipe in the room becomes the surrounding. And somebody say, okay, I study the water and this pipe together, this becomes the system, then room becomes the surrounding. So it makes sense? So anything you want to study, that is called the system. And what you don't want to study outside that is the surrounding. Make sense? It's simple. So what is system? It just depends on us. So what we want to study, that is our system. Make sense? Good. So like that. So system is just what we want to study. So we are now I'm in the slide number 8. So I am in the slide number 8 here. So I'm talking different kind of system. So let's say I have a water here. So this is a cup, and I have a hot water here. So this is hot water. The water is evaporating here like this. It's evaporating, right? It's like the tea, cup of tea, right? So you see, matter is being lost. So matter means water vapor is going out. Matter or mass is being lost. Matter is lost. And if the matter is lost, it is also taking some energy out. So energy is also lost. Energy is lost. So this kind of system is called open system. So we have a cup of water. The water is being evaporated. So some water is going out. So mass, you are using the mass, and if it is going out, some mass is going out, it is taking the energy with it, right? So this a system that losses mass as well as the energy is called the open system. Yeah. So I just talk about the loss, but it can take the energy. So maybe you have a cup of water, you can put this in a heater. So this can heat this water. So energy is coming in, and if something is here, maybe something is coming in the system. Maybe water vapor is coming into this system. So it's coming in or going out. So here I was talking about, okay, heat is being lost and matter is being lost. So this is open system. So here also the heat is coming in, the water vapor is coming in. So if the matter is coming in or going out, or if the energy and also the energy is going out or coming in the system, that is called the open system. Makes sense? Like the open cup containing hot water, right? Good. So this is a open system. Now let's talk about the closed system. Closed system. CLOSED. Closed system. Closed system. When you have a bottle of water in your bag now, so it is like this. So like this, and this lid is tight, very tight, so no water molecule is going out from there, right? Because it is very tight. So no matter how many days you put the water bottle there, the water mass never changes, right? Because the lid is very close. So you see, so the mass is not being lost. Mass is not lost. It's not lost or not going out, out, or coming in. So coming, COMING, coming in. So here, mass is not coming out because we have tight lid there, right? And the mass is not going out from here because we have a tight lid, right? So this kind of system is called a closed system. But what is being lost? So if you put a hot water here, and put for a while in the table, after a while the hot water will become cold, right? So from this wall, this is just losing heat. It's losing heat. Is losing energy or heat. Okay, so you see that? So mass is not going out or mass is not coming in, but heat is coming in or heat is going out. So this kind of system is called the closed system. Makes sense? So, for example, you have a cup here, and then you quickly cover this cup with the lid here. So no, this is a cup, right? This is a cup. So you have a lid here, and you tightly close here. So it is screwed and it's not moving. This lid is not moving, and you put this in oven. This is put in oven. What happens? So this water becomes hot because the heat enter into the system, right? Yeah, but water molecule is not escaping because we are just tightly screwed the lid here. So matter or the mass is not going out or not coming in, but the heat is going in or going out. Make sense? Good. So this room is an open room because we have an open door there, right? This is an open system. The air can go out, air can come in. Heat can come in or heat can go out, right? So this room is an open system. So this kind of system is the closed system. So I will put some homework problem or exam problem like, okay, identify which one is an open system, which one is a closed system, which one is a isolated system, kind of thing. So now let's talk about the isolated system. So you already know probably from this word, isolated system. So what is isolated system? It's just like isolation. So isolated system meaning that it doesn't interact with other things. So let's say you have a thermoflask. So this is a thermoflask here. So this is a thermoflask. So this is thermoflask. You put hot water here, right? In a hot water, we put a hot water, right? Thermoflask or hot food, hot water. And then this is closed very tightly with a cork. So it's a cork here. They put the cork is made up from the wood. So that's that conductor of heat. So this is cork here, and the wall of this thermoflask are so thick. It's a very thick wall, like this. The thermoflask wall are very thick like this, and they have some water here, right? So the heat tries to go out from this wall, but the wall is so thick, and then they make these walls with a certain kind of the material. The heat cannot go out. So if heat just try to go out, the wall of this thermoflask just reflect the heat back. So heat cannot go out. Make sense? Heat cannot go out because the wall is so thick, and they have made this wall of the thermoflask with a certain material that doesn't allow heat to go out. So if you put the hot water in thermoflask, maybe you can put the water hot for a whole day, right? So this kind of the system is called the isolated system. So the heat doesn't go out from the wall, the heat doesn't come from the wall. So make sense? And then since the lid is tight, the mass or the matter doesn't go out. So in this case, heat or energy, heat cannot go in, heat cannot go out, and mass or matter, mass cannot go in, mass cannot go out. So this kind of the system is isolated system. So it is just sitting there and isolated from the surrounding. It is not giving heat, it is not taking heat. Make sense? So this kind of thermoflask. There is no ideal isolated system. So if this cannot, the thermoflask cannot keep water hot forever, right? So maybe it works for 1 day, maybe it works for 2 days, but definitely it doesn't work after 2 days or 3 days, right? The water slowly becomes cold. So there is no perfect isolated system. So thermoflask is close to the isolated system. Make sense? So if we can make a perfect thermoflask, and I just heat a water and put in the flask and then thermoflask, and I would put that water for there, and it would remain hot forever. So that's impossible. So there is no perfect isolated system. It's close to isolated system is this thermoflask. Make sense? So open system, matter and energy coming in matter as well as energy coming or heat energy coming in or going out. In closed system, matter is not going out or in, but heat is going out or in, just like a bottle of water. And in thermoflask, heat is not going out, heat is not coming in. Matter is not going out, matter is not coming in. So that kind of system is called the isolated system. Make sense? Good. So it's very simple here. So here is in slide number 9, there is an example. So suppose we are studying a reaction occurring in a beaker on a table in the laboratory. What constitutes the surrounding? So let's say you have a beaker here, and then you are studying something here in the solution. You are mixing something, and reaction is happening. So what is the system? So what you want to study in the lab is probably you don't want to study this beaker. Because I am not very concerned about the beaker in the laboratory, right? So the beaker is not my system. So I'm just concerned about what is happening in this solution here, this solution part. So only solution part. I'm just concerned about what is the mass of this water here, of the solution here, and how much heat is being produced. What is the temperature of this one? So I'm just working within this water. So this water or the solution is my system. Solution is the system. Why? Because I just want to study the solution here. So what is the mass of the solution? What is the temperature of this solution? What is the temperature change of this solution? So I am just concerned within that part. Make sense? I don't think if you go to the lab and your instructor say, okay, measure the mass of this beaker, measure the temperature of this beaker. I don't think anybody say that, right? We are just concerned about the solution, and that solution is our system because we want to study that much, right? And what is the surrounding? Surrounding is maybe you can say, oh, this is just my boundary here, the imaginary line, or the wall of this beaker is the surrounding. So except the water, except the solution here, whatever is here is the surrounding. So for example, this is the beaker I have, and I just put it here, and inside there is water. So that water is system. So except that water, whatever is around, that is the surrounding. Make sense? Easy? Good. Now, the universe, in thermodynamics, they talk a lot about this different term, universe, whatever, but universe meaning that everything we consider is a universe, yeah? So, for example, if you say universe, what is the universe here? So this is the water, this is the beaker, and around this there are many things. So if I come all around and everything here, that is called the universe, right? So universe means system, surrounding, and boundary. They all together, if you call them, is a universe. But you really don't have to understand that one. So what is system, what is surrounding, and what is the boundary? So you will see something like this in homework as well as in exam. Yeah. So it's open system, closed system, or isolated system. Or I give the example. Okay, I have a cup of tea. I want to study only the water or the liquid in the cup. So what is the system? Is it only the tea, or it is the cup plus the tea, or it is the cup plus tea and the table where the cup is sitting? Yeah. And then your job is just to identify what is system, what is surrounding, and what is the boundary. Good. So now let's go to the slide number 10. So I am in the slide number 10. So let's say you have water here. And let's say this is a cup and this is closed. So this is closed here, and then there is a water. So if this is a cold water, so put in oven. So if you put in the oven, what happens? The water becomes hot, right? Because this from the oven, the water absorbs the heat, right? And then it becomes hot, right? So take some water from the tap and put on the oven, turn on the oven, and if you fill it, the water becomes hot, right? So water becomes hot. So what happened here? The heat go from here to here or here to here. If it becomes hot, from the heat flow from the oven to the water, right? So heat is going into the system. So let's say water is my system, and the heater is giving the water to the water, right? So heat is flowing into the system. So we give that as a plus number. Yeah. So let's say I say 100 joule of heat energy is going from oven to my system here. So I give the plus sign here. If something is heating that you want to study, the heat gained by that system is called the positive sign. It's just like the people coming from outside to this room. This room is my system. People are coming into this room is plus, right? Because number is increasing here. Yeah. So that's just like that. So so that we give the plus number. But let's say I have a hot water here. I have a hot water here, and there is ice here. Outside is ice. So this is ice here. So what happens? The hot water becomes cold, right? I have a hot water, I put in the ice. What happens? If hot water becomes cold, right? So just like the hot water, you put in the fridge and then take out and it becomes cold, right? So what happened here? So this is my system here. I am stirring this hot water and I put in the ice, and the heat goes out from this cup, from this wall like this, and this becomes cold. So maybe you lose 100 joule of heat energy from here. So I give, okay, my system lost 100 joule of heat energy. Listen. So if my system take the heat energy, I give the plus sign. If my system lost the heat energy, I give the minus sign. See, just like we have 5 people here. If 2 people go out, I will say -2. I have minus, my system lost 2 people, meaning that -2. Yeah. And if 2 people coming from outside to here, I will say, oh, I got +2 more. Make sense? +2. So if something is lost, we give minus sign. If something is gained, we give sign. Make sense? Easy, right? So good. So if the heat is going into the system, we give the plus sign. If the heat is going out from the system, what is system? System means something I am studying. Yeah. System means something I am studying. I am studying this one. If the heat is going out, I give the negative sign. If I am studying this thing, this is the system. It is coming in, so this is, I give the plus sign. That's it. Yeah. So sometimes the heat is represented by, not sometimes, most of the time, heat is represented by Q. Heat is represented by symbol Q. Represented by symbol Q. By Q. Small q or big Q. So if you write, okay, my system lost 100 joule of heat energy, I would write minus 100 joule like this. My system gains the plus 100 joule of heat energy, plus 100 joule. I would write like this. So yeah. So if you see the Q in exam or in the question paper or in the book, our book, the Q is the heat energy. How much heat energy going into the system? How much heat energy going out of the system? That's it. So Q is the symbol for the heat. Now you can give big Q or small q. It's the same thing. Now let's talk about the thermal equilibrium. So it's a pretty simple concept. Yeah. So if you read the book writes too many things. It's very complicated. The book makes overwhelmingly complicated things. Yeah. So but it's a pretty simple concept. So let's say here is a thermal equilibrium. So I'm in the slide number 11. Thermal equilibrium. So thermal means temperature. Temperature like degree Fahrenheit, temperature like Kelvin, degree centigrade, Fahrenheit, right? Temperature. And equilibrium means equal. That's it. So thermal equilibrium. Suppose you have 2 things here. So this is one thing A, and this is another thing B. So we have 2 things here, A and B. So it can be a iron block, it can be the copper block, or it can be a big copper block. It can be a small copper block. Anything. Yeah. Just take 2 things. Yeah. So there are 2 things, and then of these 2 things, the temperature is equal. So let's connect this with the wire. So you connect these two things with the wire, and you measure the temperature of this guy and measure the temperature of this guy. Both will have 25 degrees centigrade or 25 degrees centigrade, like this. Or maybe 50-50, or maybe 75-75, or maybe 1000-1000. Make sense? So what is thermal equilibrium? I have 2 things. I connect this. I bring them in touch by somehow. You can bring 2 blocks together, just smashing together, or you can just connect those with the wire, right? And then measure the temperature in both the blocks. The temperature is equal. So I say, okay, my thing A and my thing B are in thermal equilibrium. Make sense? It's pretty simple, right? So thermal equilibrium meaning that 2 or more things are there, and you are connecting together with the wire, and then you measure the temperature of each thing, and the temperature of each thing is equal. So we say that all those things are in thermal equilibrium. Make sense? So if I have 5 people, let's say if I have 5 people here, 1, 2, 3, 4, 5 people here, everybody get 100 out of 100. So all are equal. It's kind of the equilibrium, right? Just like that. Make sense? Good. It's easy. Thermal means temperature, equilibrium means equal. So if 2 or more things are here and you are connecting with some wire, or you are just putting together like this, 2 things like this, then the temperature of this block and temperature of this block are equal. Thermal equilibrium. Make sense? It's the vocabulary. Good. So here is the one point I am writing in the slide 11. So let's say this guy, this is a big block, and then it is at, I put a thermometer here, and it shows the 100 degrees centigrade here, right? Temperature. Now I have this one small block here, or you can put a big block, it doesn't matter. So this is block A and this is block B. And this is, here is a thermometer, and this says 25 degrees centigrade. So this is showing 25 degrees centigrade, this is showing 100 degrees centigrade. Now I want to connect these 2 things together. What happens? I just connected 2 things with a wire, right? So what happens? So the heat always flows from high temperature to low temperature. So imagine here is a pipe. So the wire is like a pipe, and the heat energy, temperature is not the energy, temperature is just the effect. Temperature does not flow, heat flows, and the temperature drops or temperature goes up, yeah? So what happens here, if I bring the high temperature body to low temperature body together with a connecting wire, the heat flows from the high temperature body to low temperature body. So heat here flows from, heat flows, heat flows from high temperature body, that is 100 degrees centigrade here, to low temperature body. Very important concept, temperature body. So 25 degrees centigrade. So this is the second law of thermodynamics. Heat never flows from the low temperature to high temperature body. This is a very important concept, and it is called the second law of thermodynamics. Yeah. We don't study second law of thermodynamics in our class. So it flows from high temperature body to low temperature body. Up to what time or up to what temperature it flows from high temperature body to low temperature body? So until they become in equilibrium. So here is a 100, here is a 25. So 125 would be 125, and if I take the average, that would be 64.5 degrees centigrade. So average is 64.5 degrees centigrade. So heat will flow from A to B until both thermometer will show same temperature. So it will show the 64.5 degrees centigrade, and it will also show the 64.5 degrees centigrade. Make sense? So heat flows from high temperature body to low temperature body until that point when the temperature becomes equal, or the 2 things become thermal equilibrium. Make sense? Yeah? It's pretty easy, right? So both shows same temperature. How about here? So let's take an example. I have a big ocean. I'm considering an ocean or a big lake. And if I go out now and measure the temperature of the lake, maybe it's 5 degrees centigrade now. So this morning the temperature was about minus 22 degrees centigrade. So imagine that I have a lake and I have 5 degrees centigrade water here. Big lake, tons of water here. Right? Now I have just a 1 kg iron piece here. 1 kg iron, 1 kg or 1 gram, very, very tiny. 1 gram iron piece, 1 gram iron piece, and that I heated to 1000 degrees centigrade. So what is the temperature of my 1 gram iron piece, like this one? 1000 degrees centigrade. This is 1000 degrees centigrade. And how much water here? I have this is just 1 gram. This is tons of water here, but only 5 degrees centigrade. So if this guy I put it here, like this. I put this iron piece here. Which way the heat will flow? Will heat flow from the water to this ball, or from this iron ball to water? The heat always flows from high temperature body to low temperature body. Although this has very small amount of heat, because temperature is not energy. Temperature is not, that's just the effect. The energy depends on mass. Energy is equals to half mv square or mgh, whatever those things, and energy depends on mass. If you have a very big mass, that is a very high energy, right? But this guy, 1 gram, very small mass, not much energy, but temperature is very high. But if I mix these two together, the heat will flow from temperature body to low temperature body. So that 1 gram iron piece at 1000 degrees centigrade give its heat to the water. Make sense? It's just like, I know a lot of chemistry, and you don't know that much chemistry. You're just starting, right? So the knowledge is flowing from me to many of you, just like that, right? Make sense? Yeah. So like that. So even though I'm only one, maybe my mass is small, but the temperature I have is high. So that temperature, like the knowledge is flow, the chemistry knowledge is flowing from a guy to many people, right? Make sense? So it has a small one piece, but very high temperature. Tons of water here, high temperature. So the heat always flows. If you connect these two things together by wire or just put this ball into it, the heat will always flows from that high temperature body to low temperature body. Yeah? From 100 degree to 5 degree to our, good. So it's pretty simple. Now, let's go to the 11, slide number, I think it's 12. So number 12, exothermic and endothermic process. Exothermic and endothermic process. Endothermic process. Thermic. Exothermic meaning that it gives out heat. So let's say you put, here is water here, this is water. So I have example here. It's a water here. So this is water, and you touch it, it's cold. This is water, and you touch it, it's cold, right? Now put some sodium hydroxide here. Put some sodium hydroxide, it's a base. Put some sodium hydroxide here and stick it and touch it. It becomes warm, it becomes hot. So meaning that the heat is being produced there and the temperature increases. Make sense? So if you do something and you feel that, oh, it's very hot, so that's exothermic. Make sense? So you turn the heater, your room becomes hot. So that's an exothermic process. Yeah? So the heater is giving out the heat to make the room hot. Yeah? So exothermic. So here is the water, the cold, and you put the sodium hydroxide here and you set it, and you fill it, and it becomes hot. So heat was given out. So therefore this system becomes hot. So this is called exothermic process. How about endothermic process? Let's look another example for exothermic. Let's say you have a car, you burn the fuel. You burn the fuel in car, right? So you have a car, you put the fuel in engine and you burn it and you feel hot, right? So that's also exothermic. Burn anything, burn wood or burn matchstick, burn anything, and you'll feel hot, right? So that's all exothermic process. How about the burning of fuel? It's also exothermic. Exothermic. Why? Because once you burn the fuel, you immediately feel warmth there, the hot there. So that's an exothermic process. Burning of anything is called exothermic. In the laboratory, if you mix hydrochloric acid with water, you will feel hot there. If you mix water with the, if you put sodium hydroxide in water, you will feel hot. Warm. So that's all is the exothermic process. Make sense? So we do something and we feel hot, and that's the exothermic process. So I am now talking, and my body is producing a lot of it. I'm already feeling hot. So my body heat is too much compared to the air, because I am feeling very hot here, the warmth here. So it's kind of the exothermic process I'm going through now. Yeah. So actually, all our body is exothermic. If our body is not exothermic, our body temperature would not maintain at 40 degrees, I think 39.5 degree Fahrenheit, right? Sorry, 39 degree centigrade, about 98 degree Fahrenheit, right? So how does our body maintain its heat? Because it's just continuously burning the chemical in the body and it's giving out the heat and it maintains our body temperature, right? Otherwise we will die. So our all body process is kind of exothermic. So now endothermic. How about the endothermic process? So if you do something and feel it and it feels cold, that's the endothermic process. Make sense? It absorbs the heat. When it absorbs the heat, that's the endothermic process. It absorbs heat. Previously, it emits the heat. Now it absorbs the heat. Absorbs heat. Absorbs heat. So it becomes, the system becomes cold. So take the water here. This is water. So this is hot water. So let maybe 25 degrees centigrade. Now put some ammonium chloride. So NH4Cl here. Ammonium chloride. NH4Cl. Ammonium chloride. Is it ammonium chloride? Yes, ammonium chloride, and feel it. It's now, it just doesn't feel like 25. It may feel like 5 degrees centigrade. It becomes cold. Make sense? So this is the endothermic process. Yeah. So if the water was hot at the beginning at 25 degrees centigrade, now you put the ammonium chloride and touch it, the system becomes cold, right? So this is an endothermic process because it absorbs the heat in the system and becomes the cold. Yeah, the system becomes cold. Yeah, this is good. Now the temperature go from 25 to 5 degrees centigrade. So absorbs heat. So here is another example. So here is ice. This is ice block. This is ice block. Ice block. So ice is at 0 degrees centigrade. Now I have a here I put this near my water here. So I put water here. Let's say water at 25 degrees centigrade. The heat will flow from water to ice and ice melt. So what is absorbing heat here? So water is giving heat to ice and ice is melting by absorbing the heat. So who is absorbing heat? Ice is absorbing the heat. So absorption of heat is called the endothermic process. So ice absorbs the heat from surrounding and it melts, right? So absorption of the heat from surrounding and the ice is melting is also the endothermic process. Endothermic means it's absorbing the heat. Make sense? Good. So I think we're done with the slide number 12. Now let's go to the slide number 13. So energy units. So energy units. Energy units. So if you pay your bill yourself in the home, so you already know the energy unit. And if you don't pay your bill, you can go home and look the energy bill, and they clearly write, okay, you use 400 joule heat energy this week or this month, right? Or sometimes they also not only joule, they say, okay, I have a 6,000 watt hour. Sometimes they give in the watt hour, sometimes they give in the joule, but watt hour is the most likely you see in the electric bill. So this unit is called the energy unit of heat is called joule or watt hour, something like that. Yeah. So look your electric bill when you go home and look the electric bill, and you will clearly see that in your electric bill joule or watt hour. Yeah. So we don't use a watt hour in this class. We just use a joule. Yeah. Watt hour is for a little bit advanced class. Yeah. So so energy unit is joule. Or sometimes you look this is a bottle of Coke, this is a bottle of Coke here, soda, and you look here in the label, it writes 160 calorie. So calorie and joule are the frequently used unit in class, yeah? So what does this 160 calorie mean? If you continuously drink that one, you will get fat, right? So it gives too much energy, or if the body stores too much material from there. But another kind of the soda, they write the 0 calorie here, 0 calorie. So another kind, they get 0 calorie. They didn't put any sugar here. Maybe they put some other sweetener. So that's a 0 calorie. So there is no sugar at all. And if you drink this one, you don't get energy. You can't work. But if you drink this one, you can work really hard, right? Because you are getting a lot of energy from this soda. But if you drink 0 calorie, I just taste your mouth for a while. Maybe your brain thinks, oh, okay, I'm eating or I'm drinking, but this cannot give energy, so you can't work with this one for a long time. But with this 160-calorie Coke bottle, you can work long. So sometimes you can only drink Coke for multiple days and you just keep working, right? Because you are getting the energy from the sugar in that bottle here. But here in 0 calorie, they don't have sugar. They put some stevia or whatever, stevia, stevia, whatever, those kind of things. So they give the 0 calorie. They don't digest in our body. Yeah? Good. So that's the unit of heat. So joule or calorie. So what is the relationship between joule and calorie? Sometime in some bottle they write the joule, in sometime somewhere they write the calorie. So what is the relationship between the calorie and joule? So the relation is 1 calorie is equals to 4.184 joule. So this is the relation, just like 1 mole equals to 18 grams, right? So how we convert those units is just like that. So if you say, okay, I have this bottle of Coke, this is bottle of the Coke, and the label says in this bottle I have 160 calorie food, 160 calorie food. So I want to convert how many joule of heat energy in that bottle, right? How many joule is there? Calorie is already there, 160 calorie. But I want to find what is the number of joule in this bottle. Yeah. So 160 calorie, I can just convert that is 160 calorie. So I don't need calorie. So I put this factor in such a way that I cancel this calorie. So I put the calorie down, so 1 calorie here, 1 calorie, and then I put this joule part up here, 4.184 joule here. So calorie cancel. So 160 multiplied by 4 would give you 640 joule. Make sense? So in joule, you will always get a bigger number. In calorie, you will get always a small number. Right? So 160 calorie bottle. Somebody say, in United States, somebody say, we just measure in calories. So no, you don't have to worry about it. Everybody know what is 160 calorie, what is 150 calorie. But maybe you go to India or you get another country, maybe they are writing instead of 160 calorie for the same bottle, they are writing 640 joule. That's what I am trying to tell. The bottle is same. If you express in one unit 160 calorie, and you express in another unit 640 joule, but the material is same, right? Listen, it's just like the I come from Nepal, and we just use everything in centimeter, in meter, and liter. But in United States, a lot of people use a cup, right? 1 cup. How many milliliter in 1 cup? Just like that, yeah. Or how many centimeter in 1 inch, right? So somebody express length in inch, somebody express inch in the length in meter or centimeter, right? Right? Just like that, yeah. It is different. So 160 calorie is equal to 640 joule. Alrighty, so here is a very important concept, specific heat capacity. So specific heat capacity. So specific heat capacity. I told you yesterday, if there is a heat capacity, it is independent of mass. It does not depend on mass, right? That I don't know what word yesterday we use it, but if it says specific heat capacity, it does not depend on the mass. If you see the specific in front of something, that does not depend on the mass. Yeah, so mass has nothing to do there. So what is specific heat capacity? So this is water. Take 1 kg water. You can take 1 gram, just one, yeah. Because I wanted to make it the one independent of the mass, yeah. So take 1 gram or 1 kg, and then I'm just taking 1 kg water here or 1 kg mass of anything. And what is the temperature here? Let's say temperature here is T1 is 25 degrees centigrade. So put the thermometer here. So how much water you took? 1 kg. And what is the temperature here? This thermometer is saying 25 degrees centigrade. Now heat this water, put in oven. It means put this this cup in oven and heat it so that temperature become 26 degrees centigrade. That mass doesn't change. Mass is 1 kg. Still the mass is 1 kg. Yeah. So how much heat it absorbed going from 25 degrees centigrade to 26 degrees centigrade? That amount of heat is called specific heat capacity. Make sense? So to measure the specific heat capacity, what should we do? We should take a cup. We put 1 kg or 1 gram of water there, right? And then we heat and we measure the temperature. 25 degrees Celsius. Now we start to heat it, and until when we should heat it? We should heat it. So thermometer is always there. You just put this guy in the oven, and then the temperature, when you start to heat, and the temperature increase from 25 to, it just reaches to 26 degrees centigrade, and you stop. And how much heat energy this guy absorbs going from 25 degrees centigrade to 26 degrees centigrade? That is called specific heat capacity. Make sense? Either you take 1 gram or you take 1 kg. Good. So if you take 1 kg, that has different value. If you get 1 gram, you just have to convert the unit. Yeah? Good. Any question here? Very important. Yeah? So what is specific capacity? Take 1 kg water, measure the temperature. Let's say it's 25 degrees centigrade, put in oven and start heating, and temperature from 25 to 26 degrees, just 1 degree centigrade. Yeah? Or sometimes they call Kelvin also, just convert from 1 degree Kelvin. Yeah? If it is, let's say, 300 Kelvin, heat it until the 301 Kelvin, just 1 degree Kelvin, yeah, or 1 degree centigrade, same thing. So amount of energy, so I'm going to write the definition here. Amount of energy, amount of heat needed, amount of heat needed to convert, needed to heat 1 kg of something, 1 kg mass, amount of heat needed to heat 1 kg mass, to change the temperature by 1 degree centigrade, to increase temperature, let's say increase temperature by 1 degree centigrade. Maybe a little clumsy English, but just like that, yeah. Take 1 kg mass, start to heat it, until when you should heat it, the temperature just changes by 1 degree centigrade, right? And then how much heat was that? That heat is called specific heat capacity. Make sense? Good. So it's very important, yeah. So all right. So water has a specific heat capacity. Specific heat capacity is given by C. So water has a specific heat capacity. Water has specific heat capacity of 4200 joule per kg. What does it per kg per degree centigrade? What does that mean? So if you have a 1 kg water, per kg means you have 1 kg water. Here is 1 kg water, and you want to heat it so that the temperature increase by per degree centigrade, 1 degree centigrade. So how much heat does it have? 4200 joule heat energy here. Make sense? That's what it is. Yeah. Good. So sometimes they also give in the gram 4.2 joule per gram. Sometimes they also write this. Yeah. They just divide by 1000, and this sometimes they write 4200 joule per kg. Sometimes they divide this by 1000 and they write 4.2 joule per gram per degree centigrade. Yeah. So if you take 1 gram of water, how much heat it takes to change the 1 degree centigrade? 4.2 joule. Right? But if you take 1 kg, how much heat it absorbs? 4200, right? That's what it is. Yeah? Good. Good. So this is the specific heat capacity. But how about the only heat capacity? So how about this only heat capacity? So take any amount of water. Tons of water here. I'm not taking 1 kg. I'm not taking 1 gram, right? I'm taking 2 kg, 5 kg, 6 kg, 30 gram, right? Now I heat it. So at the beginning it was, let's say, 25 degrees centigrade. Now I heat it, and the temperature of this water changes to 26 degrees centigrade. So how much heat it absorbs? That heat is called heat capacity. Make sense? To define specific heat capacity, you should take 1 gram of water or 1 kg water, right? But just to define the heat capacity, any mass is okay. Take the mass and heat it, change the temperature by 1 degree centigrade and calculate the heat, right? And that heat is called the heat capacity. Yeah? So if you take a 5 kg water, it takes maybe small amount of it. But if you take 100 kg water, it takes a lot of it, right? So the heat capacity depends on the mass. But specific capacity, you are just taking 1 gram or 1 kg, so that remains always the same. 40 to 100 joule per kg or 4.2 joule per gram. Yeah? Make sense? Good. So, what else I have here? So I think we are done. So we will do some problem based on this one in next class. Yeah. Good. Thank you very much, everyone.